Every year as we approach the time for organic chemistry exams, I often hear from students that say they are dying from all the studying that they have to do for their exams. Now fortunately, I'm over here trying to help you guys out. Now all corny jokes aside, dienes and trienes are actually very interesting organic molecules because these multiple alkene double bonds can actually work together to create some new reactivity for our dienes and trienes. Of course, we've already seen some examples of this in our allylic groups. Remember that that double bond can actually help stabilize nearby unstable sites through a process known as conjugation. Now, what do we actually mean when we say dienes? So the word dienes, of course, comes from the prefix di, meaning two, and of course our ene suffix, which refers to our alkene carbon-carbon double bond. So a diene is simply a molecule that contains two alkene carbon-carbon double bonds. Now there can be a variety of different kinds of dienes based on where those double bonds are placed. So we could have them right next to each other. So we'll have one double bond here, carbon to carbon, and then if we put our next double bond there, right, we have two adjacent double bonds. Of course, our carbon chain can continue on with whatever structure we want. We have our hydrogens attached here as well, or potentially other carbons, depending on our particular structure. Now, since our double bonds are right next to each other here, we refer to this as a cumulated diene. These are also called allenes as well. Now, allenes are a little bit interesting because since we have those two carbons both double bonded to the same central carbon, this carbon actually ends up being sp hybridized, right? So a carbon is sp hybridized when it only has two different things that it's bonded to, right? So we're only bonded to those two carbons on either side. So in terms of our orbital hybridization, we have our central carbon bonding to each of those carbons on either side using sp orbitals. So we get our head-on overlap resulting in sigma bonds. And then that leaves us with two free p orbitals. We get one pointing straight up and down, another one coming out directly towards me, and one going back away from me. And we're actually using each of these two different p orbitals to bond with our carbons on either side. All right, so this carbon might have a straight up and down p orbital that will form a pi bond with this p orbital, and our second p orbital that's coming straight out and straight back would be bonding to our other carbon over here. Again, I'm using this shading here to represent the bond, or the orbital coming straight out towards me, and the dashes are representing the other side of my p orbital going straight back away from me. The end result of this, of course, is that we get kind of this twisted system, right? So my carbon over here is going to be sp3 hybridized with all of my bonds lying in the same plane, right? So this guy is sticking like a horizontal carbon right here with my two bonds coming out in the horizontal plane, whereas this guy over here has his p orbital sticking horizontally through the marker board. And so his bonds then are going to be coming out like this, straight up and down, or not straight up and down, but coming out on either side of that carbon there. So you end up with kind of this twisted system, and this can actually result in some interesting chirality for these allenes here as well. However, these double bonds are essentially completely isolated, right? They're fixed so that they, one is at 90 degrees relative to the other, and it actually creates a somewhat unstable system overall. The next kind of diene is an isolated diene. So an isolated diene, I have an example shown here, is a diene in which our two alkene double bonds are separated by at least one or more carbons. Right? So these two bonds are separated. We have our carbon here in the middle between these two double bonds, And so our two double bonds essentially just act like normal alkenes. They don't really affect each other at all, right? These are just normal sp2 hybridized carbons. We've got them separated here by my sp3 carbon in the middle. So there's nothing really special about isolated dienes. We essentially can just treat them like normal alkenes, except that we have two different reactive sites. Now the most interesting kind of diene, which we'll be focusing most of our time on today, is a conjugated diene. So of course conjugation we talked about with allylic groups before. So conjugation is when we have double bonds that are next to p orbitals so that we can get some overlap between those different p orbitals. So here we have our double bond. So we have our double bond between these two carbons, and then the next double bond is between the next two carbons adjacent to them. So it's not like the cumulated diene where they're sharing the same carbon, but it's also not like our isolated diene where those two double bonds are completely separated. So when we look at our orbital diagram, so I have my sp2 hybridized carbon with the p orbital sticking straight up and down. I've got my 3 bonds then coming out in my trigonal planar shape. And then I have my next carbon that's going to be bonded through the sp2 orbitals. I've got the p orbital sticking straight up and down. And I can continue that for each of the carbons in my conjugated diene. So the next carbon will be back here. And so what we can notice is each of our p orbitals are all pointing up in the same plane. So we can overlap between these to make our 1 pi bond. We can overlap between these to make the next pi bond for our 2 adjacent double bonds. But you can notice, of course, that these central carbons also have their p orbitals sitting right next to each other and potentially overlapping. Right? So this is our conjugation again, where when we have those p orbitals all sitting on adjacent carbons, right? So all 4 of our carbons through our conjugated diene are all sp2 hybridized, and so they all have those p orbitals that are able to overlap in this conjugated system. So we refer to these as conjugated p orbitals or conjugated pi bonding. So our electrons are actually able to be kind of shared between these different p orbitals, and that stabilizes our system overall. Right? So we can share out those electrons and help stabilize all of our carbons through this kind of communal sharing of our electrons here. So even though all of these molecules are dienes, right, they all have 2 double bonds, we actually have a significant difference in our stability of these different dienes just based on where we're placing those double bonds. So our accumulated diene is actually the least stable. So I mentioned that this kind of twisted system where we have our central carbon that has both double bonds to the same carbon, but neither of our double bonds are able to help each other out since they're rotated 90 degrees relative to each other. This one is the least stable. Our isolated diene has moderate stability. It's essentially the same as any other alkene. But our conjugated diene is the most stable because those 2 double bonds are able to work together and help each other out through kind of sharing our electrons through this conjugated system. As we've seen, our conjugated diene actually has increased stability because of the sharing of electrons between those adjacent p orbitals. Now the question, of course, then is, how does this affect our reactivity? Right? Normally things that are more stable tend to be less reactive, but in this case we have 2 alkenes, so you should think that we have double the reactivity of a normal alkene, right? So to look at this reactivity, we're going to see what happens when we try to do a typical alkene addition reaction. So our hydrohalogenation with our hydrogen halide here of our hydrogen bromide in this case. So in our normal hydrohalogenation reaction, of course, we're using the extra electron density in our double bond. So we're going to take our hydrogen from our strong acid here in the first step of our hydrohalogenation reaction. So of course that will add on our hydrogen here at the end and produce our carbocation here in the middle. This is of course because we have our Markovnikov's rule, of course, which dictates that the carbocation forms at our more substitute position to then allow that more stable carbocation. So in this case, of course, we could then, if we're doing a normal hydrohalogenation reaction, we would take our bromide ion and we would attack that carbocation, and that would give us our product here with our bromine added on to that more substitute position and our hydrogen added on at the end in our less substitute position. Of course, I'm only showing the new hydrogen that was added on. We would still have the two hydrogens here that we started with in our initial molecule. So in this reaction here, we followed our normal hydrohalogenation mechanism using our diene, right? We just reacted with that first alkene as if it was a normal alkene without any other alkenes sitting next to it. So in this case, we're only reacting at that first alkene, right? So if we number our carbons 1 through 4, we say that we added on to the first carbon, right? Because that's where our hydrogen went, and our bromine, of course, went on the second carbon. So we call this a 1-2 addition. So it's 1-2 addition of our hydrogen halide. Now if we look at our carbocation intermediate here, though, you should remember that whenever we have a carbocation next to a double bond, we actually have resonance here where our double bond can move over to help to spread out that carbocation and stabilize that carbocation. So if we do this little shift here, instead of just attacking with our bromide ion, we then get our double bond here in the middle and our positively charged carbocation over here on the left side. So this would be carbon 4 using my original numbering system. So of course this would be two different resonance structures, right? So these can easily convert back and forth. Again, we should think of this as being really more of a resonance hybrid, where we have partial double bonds between all three of those carbons and our shared positive charge between both of those two carbons, right? So our positive charge gets shared out, and that helps to stabilize that carbocation overall. So we have kind of two different resonance structure intermediates and our overall resonance hybrid in the middle. Now, of course, as we look at our resonance hybrid, and as we look at these two different contributors to our resonance hybrid, you should note that we have then two different sites with positive charge that would both be electrophilic sites. So in our initial reaction, we attacked that electrophilic site on the right, but we also have an electrophilic site here on the left that we could attack as well. So our bromine could come in here as our bromide ion and attack as our nucleophile to that electrophile. And now this would produce a slightly different product from our original 1-2 addition product. So our bromine ends up down here at the end, and now our double bond actually ends up here in the middle of our 4-carbon chain. Our hydrogen still ends up way down here at the first carbon. So we added our hydrogen on the first carbon. Our double bond is now in the middle at the second and third carbons. And our bromine here is at the end here on our fourth carbon. So in this case, this would be a 1,4 addition. Right? Because we added our hydrogen to the first carbon and our bromine to the fourth carbon. So if we have two different products, how do we know which product is actually going to form, or which one will be the major product and which will be the minor product? Well, again, of course, whenever we want to determine what products are most likely to form, we want to look at a couple of different things. We want to look at the stability of our final product, right? The more stable a product is, the more likely it is to form. But we also want to look at the stability of our intermediate. The more stable the intermediate, the more likely that product is to form. So let's start over here at our product. So if we look at the 1,2 product, the main thing that we can look at here in terms of stability is our alkene double bond. Now you might remember that alkenes are stabilized by hyperconjugation from adjacent carbons. So the more carbons that we have attached to that alkene, the more stable that alkene will be. Here we have one carbon connected directly to our alkene. So we refer to this as mono-substituted. Our alkene down here, so our alkene is now in the middle. We have a bond to a carbon over here, and we have a bond to a carbon down here. So this is actually a di-substituted alkene. Now, as we increase that substitution, we increase the hyperconjugation, and therefore we increase the stability of our alkene. So this is actually going to be more stable than our 1,2 addition product. So if this is more stable, this should be our desired product, right? Well, we haven't looked at our intermediate yet, right? So this is the more stable product, but the intermediate will also affect which product is preferred. So if we look at our intermediate, so again, of course, we have this resonance hybrid, where we say that, okay, the positive charge is shared between the two, we have partial double bonds there, but these resonance contributors aren't identical. So they don't necessarily contribute equally to our resonance structure. And so that in turn would mean that our positive charge isn't necessarily equally shared between both of those carbons. Right? It might not be exactly half a charge there and half a charge there. It might be more like 60% of a charge here and 40% of a charge there. So as we look at our intermediates, so our intermediate, of course, is a carbocation. And carbocations, again, their stability is based on substitution because they get that hyperconjugation from adjacent carbons. So our carbocation up here, of course, would be a secondary carbocation. It's stabilized by both of those two carbons adjacent to it. Our carbocation down here is a primary carbocation. It only has that one carbon attached to stabilize that carbocation. So this resonance contributor is more stable, and so that means that we'll actually get more of our charge here than we will at the fourth carbon here at the end. So it won't actually be a perfect 1/2 to 1/2 share. We'll get slightly more positive charge here, and we'll end up reacting more through our more stable intermediate to produce this product here. Now at this point you might be feeling a little bit confused, right? So I just told you that this product was more likely to form because it's the more stable product, but this product was more likely to form because it has the more stable intermediate. Now the truth is that both can form, but it just depends on the environment that we're doing our reaction in. The main environmental effect that we're going to consider is the role of temperature in this reaction. Now, as we've seen previously, when our intermediate is more stable, that will actually speed up our reaction. Right? So the stability of the intermediate determines the height of our transition state on our energy diagram. And of course, the height of that transition state tells us how likely we are to have enough energy to get over that hill and get down to our product. Right? So here we have a higher transition state. Here we have a lower transition state. Lower transition state, it's easier and faster to go over that and get to our product. So our 1,2 addition product is the faster product, right? Where we can produce that more quickly. So when we say that this is more likely to be produced because of our secondary carbocation intermediate, what we're really saying specifically is that our reaction to make this will be faster. Now again, over here we already said this is more stable. So this reaction will be slower because it goes through our less stable intermediate, but it gets the better product overall. So now if we consider the role of temperature, so temperature of course determines how much energy we have to get past these unstable intermediates to get to our products. If we have a lot of energy, then the stability of our intermediates isn't as important, right? Because we have plenty of energy to get quickly through these intermediates and get to our products. In that case, we want that more stable product as compared to our less stable product. So at high temperatures, when we have lots of energy and don't really have to worry about our reaction getting slowed down by that unstable intermediate, we're going to prefer our 1,4 addition. If we have lower temperature, we'll have less energy, and so it's going to be even harder to get over that higher barrier that we have for our less stable intermediate. So at that point then, at lower temperatures, we're going to prefer our faster reaction. Right? So our 1,2 addition will go through that more stable intermediate, and so we can more quickly produce this, even if we don't have as much energy to get over that activation energy barrier. So to summarize then, if we use lower temperature, our 1,2 addition product will be the major product. If we use higher temperatures, our more stable 1,4 addition product will be our major product. So we can actually control which product is produced just by changing the temperature. Now this sort of 1,2 or 1,4 addition to our conjugated diene can also occur for other alkene addition reactions. So here we have our halogenation reaction. We're adding diatomic bromine onto our simple conjugated diene. So again, we'll expect 2 different possible products. We can either add that bromine to the first carbon and the second carbon in our 1,2 addition. Or we can add them to our first and fourth carbon in a 1,4 addition. So we get our double bond in the middle. And again, of course, as we label our carbons, we can clearly see that our 2 bromines are added on at either end of our carbon chain at that first and fourth position. Now in this case, of course, we don't have our normal carbocation intermediate. Instead, we have that halonium ion cyclic intermediate. And so the slightly different structure of that intermediate actually leads to our 1,4 addition product as our dominant product, or the major product in our reaction. So we still have maybe some mixture of 1,2 and 1,4, but 1,4 is always going to be favored, and it's not as much temperature dependent. At the beginning of this lecture, I also mentioned the possibility of trienes. Right? So trienes can be conjugated similar to dienes, and then we can get that added stability and reactivity like we saw with our conjugated dienes. The most common example of a conjugated triene is our aromatic benzene molecule. These aromatic molecules have extra stability because of that conjugation. They also have extra reactivity as well. This makes them incredibly important in both organic chemistry and biochemistry. Some of our most important biomolecules, DNA, is actually made from aromatic ring structures. So we'll take a deeper look at those later. But for now, just know that they do have some similarities to our conjugated dienes in the sense that they have those p orbitals next to each other that are going to be able to share electrons to change our reactivity and our stability.